In this video, we will see the suggestion for week 9, assignment 9 for the course Principles of Communication Systems 1. First question, T1 system is an example of. So, T1 is an example of TDM, time division multiplexing. TDM, time division multiplexing. Consider a superhead receiver with a broadcast frequency FC equal to 2 kHz and intermediate frequency FIF equal to 1 kHz and corresponding local oscillator frequency that is larger than FC is given as. So that is, intermediate frequency equal to local oscillator frequency minus FC, or local oscillator frequency equal to intermediate frequency plus FC, that is equal to 1K plus 2K equal to 3 kHz. 3 kHz. Third one, 19 voice signals are sampled uniformly and then time division multiplexed. The sampling operation uses flat top samples with 4 microsecond duration. The multiplexing operation includes provision for synchronization by adding an extra pulse of sufficient amplitude and also, which is also 4 microsecond duration. The highest frequency component of the voice is 5 kHz. Assuming a sampling rate at NIQ state, calculate approximate silence time between successive pulses. So silence time between successive pulses, 19 signals plus 1 sync pulse. So sampling period Ts equal to 1 into 10 kHz, which is equal to 0.1 milliseconds. This is equal to 1 frame including 1 sync pulse. Okay, now this is equal to, so time duration equal to 19 into 4 microseconds plus 1 4 microseconds for the entire for the pulses is 80 microseconds. So remaining time duration is 0.1 millisecond is equal to 100 microseconds minus 80 is equal to 20 microseconds. So silence time duration is approximately 20 microseconds by 19 to 1.05 microseconds, which is approximately equal to 1 microseconds. 1 microseconds. So consider a super hetero receiver with broadcast frequency FC and intermediate frequency Fi. The corresponding image frequency is given as. So image frequency definition. Image frequency is defined as Fsi equal to Fc plus 2 times intermediate frequency. So this is the definition. Fourth one. So Fc plus 2Fi. Fc plus 2Fi. Fc plus 2Fi. Fifth one. Consider a super heterodyne receiver with the broadcast frequency FC equal to 1 kHz and intermediate frequency is 500 Hz. The corresponding image frequency is given as. Fifth one. So image frequency definition as it is given in the problem 4 is Fsi equal to Fc plus 2Fi. Fc they have given 1 kHz and Fi they have given as 500. So this is equal to 1K plus 1K, 2K. 2K. Now sixth one, consider signals MIT. So 5 signals are there, M1, M2, M3, M4, M5. So with the various sampling frequency and various band limited highest frequency component. We will see now the solution for this one. So L equal to 1024, which is nothing but 10 bits quantizer. Mu law is a 10 bit quantizer. We will see what is this bit rate. So M1T is band limited to, they have given 4 I square. So I is equal to 1, 4 kHz. So sampling rate for this is 2 times NIQ state, which is 8K. For M2 frequency, the highest frequency component is 16 kHz. That means the sampling rate is sampling frequency is 36 kHz. For M3 it is 36 kHz and 72 is the sampling rate. And for the M4 it is 64 kHz and sampling rate is 128 kHz. And for the last one M5, the highest frequency component is 100 kHz. Therefore 2 times 100 is 200 kHz. Add all these frequencies, you will get 440 kilo, that means samples per second. These many samples will get samples per second. So into number of bits, this is number of samples. 440 into 10 power 3 is the number of samples per second into the number of bits, that is equal to 4.4 mbps. What is the minimum sampling rate required to avoid aliasing for the signal m of t? M of t equal to sync 3 10 3. So m of t they have given is sync cube 10 3, sorry 10 t. So now we know that for a sync function, this is the this is in frequency domain, so which is shown here as a rectangular pulse, okay. That means w is the bandwidth for a sync function. So now here 2w t is equal to 10 t from the given equation. So therefore w equal to 5 hertz, w equal to tt cancels, and then w equal to 10 by 2 is equal to 5 hertz. So w is equal to 5 hertz. Now first what we'll do here is we'll consider two sync function, which is multiplication of two sync function, okay, and the convolution of this will be the output will be the convolution. In the frequency domain it becomes a convolution, therefore the bandwidth will be equal to double the bandwidth of the original signal. So 2w, original signal bandwidth is w, so the after convolution the bandwidth is doubled, 2 times w. And now again what I'll do is I'll again do convolution with m1. This is m1, this is equal to is missing here, m1 is nothing but a sync function with another sync function. So now there is one more times we have to multiply the sync function, so we'll get sync cube. Now if I multiply m1 with the sync function, this function m of t becomes sync cube. But what about in frequency domain? Frequency domain now becomes x of f, which is for the then x1f, and then this x of f. So we already have 2w here, so another convolution will give you 3w, but w is equal to 5, so the according to Nyquist rate, minimum sampling rate equal to 2 into 3w. So 2 into 3 into 5 is 30 hertz. So in a super heterodyne receiver with intermediate frequency f2, what is the frequency of the local oscillator corresponding to the incoming signal of carrier frequency f1, eighth one. So eighth one, local oscillator frequency equal to intermediate frequency plus the fc carrier frequency. Here intermediate frequency equal to f2, they have given in terms of f1 and f2, and fc is equal to f1, therefore fl equal to f2 plus f1 or f1 plus f2, f1 plus f2d, f1 plus f2 or f2 plus f1. Now ninth one, the bit rate of T1 system is approximately, so bit rate of this system, so we can bit rate is equal to number of bits in a frame divided by sampling period. So the number of bits we can calculate it as 193, which is already discussed in the lecture 193, and the sampling time is 125 microsecond, which is also discussed. This entire problem is already discussed in the lecture. So we get it we get as 1.544 megabits per second. This is according to the lecture. And number of, how to calculate number of bits in a frame? So 24 channels are there, 24 in a T1 system, 24 into 8, so we'll get 192 plus 1 sync 193, totally there is 193. The answer is 1.544. Last one. Consider a uniform quantizer with 256 quantization level and maximum message amplitude 500. What is the approximate quantization noise power? So 10th one. So quantization noise power is delta square by 12, where delta is subsize. This can also be written as 1 by 3 m max square by 2 power 2n. In terms of log, 10 log, take logarithm on both sides and multiply by 10. Then this becomes minus 10 log 3, 20 log m max minus 10 log 2 power 2n. And then this can be written as minus 4.771, because log 3 is 0.477 multiplied by 10, you will get 4.77. And here this one log of 500 multiplied by 20 is 53.98. This is plus, and 6 into n is the number of bits, 256. So 256 is nothing but 2 power 8. So 8 bits. So 6 into 8 minus 48. This becomes minus 48. So we will get 1.21 dB. 1.21 dB. Okay. Thank you, viewers.